In this lesson, we're going to look at something called the Pearson Product Moment Correlation Coefficient, or PMCC for short. The PMCC measures how strong a correlation is in a scatter graph, or how strong the correlation is between two variables. So in this scatter graph, R equals -1. Our PMCC equals -1. So when a correlation coefficient is equal to -1, it means that all the points in the scatter graph would lie in a perfect straight line with a negative correlation, so the straight line has a negative gradient. So that's the most extreme case when R equals -1. And R can go all the way up to +1, which would be this example, where the points lie in a perfect straight line but with a positive correlation. And the way that R is calculated means that R can't go beyond 1 or -1. It's always going to be on this spectrum between -1 and 1. In the middle, you've got a scatter graph that looks like this, where there's absolutely no correlation at all. So let's write that down. So we've got strong negative when it's equal to -1, and we've got a strong positive when it's equal to 1. And in the middle, we've got no correlation. And if we have a graph that's in between, then the closer it is to -1, the stronger the negative correlation, and the closer it is to 1, the stronger the positive correlation. And you can see that in these two examples here. This one is a weaker positive correlation, and this one's quite a strong negative correlation because the points nearly lie in a straight line. Well, we don't actually need to be able to calculate this PMCC because we're always going to use our calculators in the exam. But I think it's useful to have a look at the formula and work out why is it 1 strong positive and why is -1 strong negative. So we're going to ignore the denominator for a while, and we're just going to look at this numerator. So what this means is for each data point, we're going to work out this value, x minus x bar multiplied by y minus y bar. Well, I've got a scatter graph here, and I've put down through the middle of the x values, I've put x bar. And through the middle of the y values, I've put y bar. So that gives me my sort of middle of the data is here. Well, let's think about what would happen when I calculate x minus x bar times y minus y bar for some of these points. So let's look at this point up here, for example. Because this point is to the right of x bar, x minus x bar is going to be positive. And because this point is above y bar, y minus y bar is also going to be positive. So when I calculate this numerator for this point, it's going to have a positive contribution. And we could do a similar thing for a point down here. This point is to the left of x bar, so x minus x bar is going to be negative, and it's underneath y bar, it's less than y bar, so y minus y bar is also going to be negative. So when I times these two brackets together, I'm going to have a negative times a negative, which is a positive. So this point's also going to have a positive contribution to the sum. Let's look at a point in this quadrant then, such as this point. Well, because it's to the right of x bar, x minus x bar is going to be positive, but it's underneath y bar, so y minus y bar is going to be negative. So I'm going to have a positive multiplied by a negative, and so this point is going to have a negative contribution to the sum, to that numerator. And we could do a similar thing for this point and would find that this one has a negative contribution. So when we calculate this numerator, we add up each of these contributions from these points. So you can see that the more points you've got in this top right quadrant and bottom left quadrant, the stronger the positive correlation. And also the more positive contributions you're going to have. If you've got lots of positive contributions, and you've got a strong positive correlation because they lie in these two quadrants. So the sum is going to become closer to 1. And similarly, if you had lots of points in the negative contribution quadrant, then your correlation coefficient would be closer to -1. And we don't need to worry too much about this denominator, but that denominator basically makes sure that it can't go further than -1 or 1. So let's look at example 2. In example 2, we're actually given some data from the large data set, which is daily mean wind speed measured in knots and the daily maximum gust, which is also measured in knots. And it says they were recorded for 10 days in September in this place in 1987. So in part A, it says state the meaning of NA in the table above. So NA stands for non-applicable, and this means that we don't have data for this day for the wind gusts. So it means there is no available data for the gusts on those 2 days. And in part B, it says calculate the product moment correlation coefficient for the remaining 8. So when we do that, we're going to have to ignore this data because we don't have the data for the wind gusts. So let's cross that out. We sort of cleaned up the table a little bit. So in order to do that, we're going to have to use our graphical calculators. We're not expected to use the formula in our exam. And actually that saves a lot of time. So what you need to do is you need to go to your calculator, and if you start on menu, you need to go to statistics, and then in list 1 you need to put the data for the W, which is the mean wind speed, into list 1. And then into list 2 you need to put the data for the maximum wind gust, remembering that we've crossed out those 2 days where we don't have data for the wind gusts. And then what we need to do to calculate the product moment correlation coefficient is we need to go on calc, so F2, and then we need to go on set before we do anything else. And we need to just make sure that where it says 2var, 2 variable means we're working with a scatter graph. The X list is list 1 and the Y list is list 2. And that's just telling the calculator where the X data is and where the Y data is. And it doesn't actually matter which order you do that in. But let's leave it as list 1, list 2. And leave 2var frequency as 1. Just make sure that it's 1. And then we're going to go on reg for regression. Regression basically means a line of best fit. And once we've clicked on reg, we're going to click on X, and we want AX plus B. Well, what this actually does is it draws a line of best fit through the data using a formula, and it gives us the equation of the line of best fit. So we know that the gradient of the line of best fit is 2.5, and the y-intercept would be 1.8. But what we're interested in this value of R. And that's our PMCC, our product moment correlation coefficient. So R equals 0.95 to 2 decimal places. So let's go back to the example. we can just write down r equals 0.95. You don't need to show any working out because the exam board know that you're going to use your calculator. And then in part C, it says, with reference to your answer in part B, comment on the suitability of the linear regression model for this data. So linear regression model basically says, how good is the line of best fit? Or another way of thinking about that is, how good is the correlation? How well correlated is this data in a line? So remember our scale, R goes from -1 all the way up to 1, with 0 being no correlation. Now we're at 0.95. Now remember that 1 was a strong, very strong, in fact perfectly strong in a line, positive correlation. So 0.95 looks like it's pretty good. So we can write a sentence to explain that. 0.95 is close to 1. So the data has a strong positive correlation. This means the linear model is suitable. And it might be worth just looking at what some of these terms mean. So linear regression model means that we've taken our data, we've got wind speed against gust, mean wind speed against gust, and what we've got is we've got our data points and we've tried to draw a line through them. And that's what the calculator's done. And we've got a fairly strong positive correlation, which means that our line is good. Now, if we had our product moment correlation coefficient closer to 0, then perhaps our data would look more something like this. And that would mean that our line of best fit probably isn't a very good model for a line going through the data.